Algebra revision for differentiation. So there are three things we're going to look at in this worksheet, which are factorization, indices, and logs. So these are going to be really important for kind of our foundation differentiation. So it's just a recap on what we've done up to this point, so that when we go to start delving into our differentiation, that we don't have to spend too long reminding ourselves how to factorize or how to use our indice rules or how to use our log rules. So in question 1 here, we're looking at factorising the following from A to F. So we're going to start with the first one, which we can see is just a standard quadratic equation. So what we have is 2x squared plus 9x plus 4. And again, you can factorise this whichever way you prefer. So as you know already, I always do it by the traditional route, which is taking our coefficient of x squared and multiplying it by the last term, the constant. So in other words, 2 times 4 gives us 8. And then we look at this number 8 and we see what are the factors of 8 that will add to give us this middle number here, 9x. And of course, it's going to be 8 and 1. So when the signs are different, you always have to check, do they multiply to give you the correct number and also the correct sign? And do they add to give you the correct number and the correct sign? And of course, plus 8 times plus 1 gives us plus 8. And 8 plus 1 gives us 9. So we then take these two factors and we take 9x and we separate them out into those two factors. So in other words, we have, this is equivalent to 2x squared plus 8x plus x plus 4. So in other words, if we just look back there, we can see that the 8x and the x will give us the 9x. Okay, so what we then want to do is we want to take our first two and take out the highest common factor. So we're grouping the 2x squared and the 8x. So the highest common factor there is 2x. If I take out 2x from 2x squared, that leaves me with x. And if I take out 2x from 8x, that leaves me with 4. If I then look at the next two, we have x and 4. And there's nothing common there other than 1. So my highest common factor is 1, leaving me with x plus 4. So in other words, I've taken out my highest common factor there. So now I can see, again, I have another highest common factor, which is x plus 4. So if I take out x plus 4 as being common, that then leaves me with my 2x and 1. So I have now fully factorised 2x squared plus 9x plus 4. So if we look at B then, we'll have the same process. This time we have a negative sign in here. So we have 4x squared minus 23x plus 15. So again, what I want to do is take the coefficient of x squared and multiply it by the constant. So we have 4 times 15 gives us 60. And I then want to look at the factors that multiply to give me 60 and then add to give me this middle number. But this time it has to be minus 23. So of course you can have 6 times 10 and 5 times 12. But if I look, I want to get 23. So I can see that I have 20 times 3 will give me 60. And 20 and 3 will add to give me minus 23. But of course it has to add to give me minus 23. So it must be minus 20 and minus 3. And of course I have to then check, do they multiply to give me plus 60? And of course minus 20 by minus 3 gives me plus 60. So we then go and we take these two factors and I replace minus 23x with my two factors there, minus 20 and minus 3. So we end up with 4x squared minus 23x plus 15 is equivalent to 4x squared minus 20x minus 3x plus 15. And of course, we'll remember that it doesn't matter which order I put in the two factors. I can have the 3 and the 20 the other way around. And it should be 3x. And it'll still work out. It'll still factorise out the same. So again, we're grouping the first two. And then grouping the second two. And taking out again my highest common factor. So what we have is 4x is my highest common factor, leaving me with x minus 5. And then I can see that 3 is common between 3 and 15. So, of course, it has to be minus 3, because that'll leave me with x minus 5. So if I took out plus 3 there instead of minus 3, what we'd be left with is minus x plus 5. And, of course, we want these two brackets here to be exactly the same in order for me to take out my highest common factor a second time. Okay, so we're always looking for the highest common factor and the highest common factor. Okay, so I can see if I take out x minus 5 as being common, well, that leaves me with 4x and minus 3. And that is fully factorized. Okay, so if we look at C, it's a little bit different because it's x squared minus 64. There's no x term here. So even though it looks like a quadratic, I'm not going to be able to factorize it the way I have done A and B. But what you should notice there is that we have x squared minus 64. So if I go on to the next page, we have x squared minus 64. You should hopefully spot is the difference of two squares. Now, of course, this is not in your maths table, so you need to know this off by heart, this formula. So big fat NB next to this one. Our difference of two squares is given by x plus y, x minus y. So we say NB, not in tables. So we have to take x squared minus 64, and we're going to write it as something squared minus something squared. So, of course, x squared is x squared, and 8 squared is 64. So essentially that's the x in the formula and the y in the formula. So in other words, I'm going to put x and y into this formula here. So that gives me x plus y, in other words, x plus 8, times x minus y, so in other words, x minus 8. And therefore that is fully factorized. So again, if we go back and check, if ever you want to make sure you've factorized it fully, if you multiply out those brackets quickly in your head, you should end up back where you started. So if we go back to the previous page, we then have D is 3x squared minus 75. So we have 3x squared minus 75. So again, we might look at this and go, okay, that looks like C. So it's x squared minus y squared, the difference of two squares. However, this time, what you might notice is that I can't say something squared minus something squared because, of course, there's nothing that you can square that will give you this number here. 3 is an answer. So that's an issue. So if you can't get something squared minus something squared, check, can you factorize first? So if I take out 3 as being common there, that leaves me with x squared minus 25. And now what you'll notice is inside the brackets is, of course, our difference of two squares. And we can proceed like we did in C. So in other words, what we have is 3 times something squared minus something squared. And of course, x squared will give us x squared, and 5 squared will give us 25. So that will be our x in the formula, and 5 will be our y in the formula. So that gives us x minus y times x plus y, or x plus y times x minus y. It doesn't matter which way we say it, because of course, multiplication, the order doesn't matter. So therefore our answer fully factorized is 3 times x plus 5 by x minus 5. Okay, so if we look at E next, E is x cubed minus 216. So again, might look a little bit like our difference of two squares, but of course this time we have a cube. So it is, of course, going to be our difference of two cubes. And again, our difference of two cubes is not in our tables. So again, we have to know this off by heart as x minus y times x squared plus xy plus y squared. So again, we say NB not in tables. Okay, so again, we're going to start by saying x cubed minus 216 is equivalent to saying something cubed minus something cubed. So of course you can use your cube root on your calculator if you can't see what number is going to cube to give us 216. And of course, if you put it into your calculator and you get the cube root of 216, you'll see that we have 6 is the answer. So in other words, 6 cubed is 216. So 6 by 6 by 6 is 216. So in our formula, x is x and y is going to be 6. So that's going to be x minus y, so x minus 6, times x squared plus x times y, so x times 6, plus y squared, in other words, 6 squared. So we have to be very careful when we're subbing back in here. You'll see that I'm using brackets, and this is because it's not always going to be x cubed. It could be anything in brackets there to be cubed. And you have to make sure that you're subbing in correctly into that formula, that it's the first term squared plus the first term times the second term plus the second term squared. So let's simplify out that bracket. So we have x minus 6 times x squared, which is just x squared, x times 6, which is 6x, plus 6 squared, which is 36. And this is x cubed minus 216 fully factorised. Okay, so our last factorising there then is f, which is 8x cubed plus 125. So if we write that out, we have 8x cubed plus 125. And again, looks like the difference of two cubes, but of course is the sum of two cubes. So we have x cubed plus y cubed is equal to x plus y times x squared minus xy plus y squared. And again, sum of two cubes, same as difference of two cubes and difference of two squares, is not in our tables, so it needs to be learnt off by heart. Very few formulas that are not in our tables, but these three are not. So you do have to know them off by heart. Okay, so again, let's see. Can I write it as something cubed plus something cubed? And if I can't, then again, I would take out my highest common factor. But of course, 2 cubed gives us 8. So this time what we have in our first bracket is 2x. And 5 cubed gives us 125. So if I now apply that to my formula, 2x will represent x in the formula, and 5 will represent y in the formula. So what we have is x plus y, so that's going to be 2x plus 5 times x squared, which is going to be 2x to be squared, minus x times y, so that's going to be 2x times 5 plus y squared, in other words, 5 squared. Okay, so again, just double check when you were doing these questions, did you sub correctly into the formula? Because often this is where people make their mistakes here. They'll put in 2x squared instead of 2x to be squared. And of course, when I square 2x, I get 4x squared. So sometimes people will have 2x squared there instead of 4x squared. And of course, 2x times 5 is minus 10x, and plus 5 squared is plus 25. So that is fully factorised. Okay, so next on our sheet then is indices. So for indices, you can see here that I'm advising you to use page 21 in our maths tables. And with page 21 in our maths tables, you'll see that on the left-hand side, we have our indices. And on the right-hand side, we have our logs. And in the middle, we have our logs as well. So for question 2, we're really kind of focusing on this left-hand side here of page 21. So that's page 21. And the first thing we're looking at here is the square root of x. So you can see here, I'm asking you to write it as x to the power, where the power can be anything from a natural number, an integer, or a fraction. In other words, it's one of the rationals will be the power. Okay, so let's look at the first one, the square root of x. So generally we know this will kind of off by heart, but if we don't, we need to see which rule am I using. And you'll see that the rule I'm using is this one here. So you can see it's q root a is equal to a to the power of 1 over q. So there is no number there, but square root implies that it is actually the second root. So that can actually be written as, it's equivalent to root x. Okay, so therefore that means that the q in the formula there is the number 2. And a is the letter x. So it's the letter underneath the square root. So therefore, if I'm looking at the rule, it tells me to write it as a to the power of 1 over q. So a in this case is x to the power of 1 over q, and q is 2. So in other words, root x is x to the power of a half. So then if we look at the second one, I followed on from that, where it's the cube root of x. So again, same rule, still looking at this one here, q root a. So again, we would say q in this case is 3 and a is x. So therefore the cube root of x is equivalent to saying a to the power of 1 over q. In other words, x to the power of 1 over 3. Now if we look at c then, we have the fourth root of x to the power of 5. So I'm just going to do that on the right hand side here. So we have the fourth root of x to the power of 5. So in this case, we now actually have another power to deal with. So let me just erase this red line here on the Metz tables. So this time we have the a to a power underneath the square root. So that's actually going to be the one directly underneath that we're looking at. So you can see here it's a to the power of p, and it's the q root of that. So in other words, what I'm saying is that if I look at that formula, q this time is the fourth root, and the power of a is 5, and a is equivalent to x here in this question here. So therefore, if I apply the rule there, it says that if I have the q root of a to the power of p, then that can be written as a to the power of p over q. So in other words, a here is x, p is the power, 5, and the root is 4. So that's going to be x to the power of 5 over 4. So the top is always the power and the bottom is always the root. Okay, so if we look at d is 1 over x. And again, this is one we tend to always know off by heart. So 1 over x, how can that be written as x to a power? So again, if I look at my tables, page 21, and let me just erase that last rule we were looking at. This is 1 over a to a power. So therefore, a is x, and the power is 1 in this case. So that's the same as saying 1 over x to the power of 1. So therefore, that's going to be written as a to the power of minus p. So in other words, x to the power of minus 1. Okay, so if we look at e then, that looks similar to d. It's 1 over x, but it's 1 over root x this time. So if I go on to the next page there, e is 1 over root x. So this is combining what we just did there a second ago. So we have 1 over, which is this one here, and we also have a root. So we're combining these two rules that I've just underlined. So in other words, what we're saying is that we have a is going to be x, and p, our power, is going to have to be 1 underneath the square root there. But of course, it's the square root. So in other words, q is 2. So in other words, this is going to be a to the power of minus p. So it's a to the power, x to the power of minus 1 to the power over q, which is 2. So this 1 over the square root of x is x to the power of minus a half. So the next one then is 2 over root x, which is f. So 2 over root x, right, that is exactly the same as saying 2 times 1 over root x. And we've actually just written 1 over root x as x to the power of minus a half. So in other words, that's the same as saying 2 times that, which is just 2x to the power of minus a half. So always be careful with those ones. If there's a constant on the top, just remove it and break down the rest of the question. It's always a lot easier. Okay, so G is 2 over the cube root of x. So again, we're just building it up gradually until we get to the ultimate question. So EFG. So 2 over the cube root of x. So same as again, take out the 2, which leaves us with 1 over cube root of x. And of course, what have we got? Well, the root is q is 3, a is x, and the power of x there is just 1. So that becomes 2 times x to the power of minus a third. So in other words, 2x to the power of minus a third is another way of writing 2 over the cube root of x. Okay, and the last one then, the ultimate one, is h. So it's 2 over the cube root of x to the power of 5. So I'll just do it here on the right hand side. So we have 2 over the cube root of x to the power of 5. So again, that's the same as saying 2 times 1 over the cube root of x to the power of 5. So again, what's a? Well, a is x. What's the power? The power is 5. And the root is 3. And of course, the 1 over is giving me this negative sign. So in other words, that's 2 times x to the power of minus 5 over 3. So in other words, that's 2x to the power of minus 5 over 3. So the minus power always comes from 1 over. So if ever we have 1 over something, there'll always be a negative power. Okay, so that's a little recap on our indices using all of these rules here on page 21 of our maths tables. So we just touched on 1 or 2 of those little rules that are the ones that are going to come up quite regularly in differentiation. So the last section of this revision sheet then is our logs. So again on page 21 in our maths tables, we're going to be using these to simplify or expand our logs. So again, really important for differentiation that we can do this. It's going to make some of our more complicated looking functions to differentiate a bit easier when we apply our log rules, whether be it expanding or separating it out or simplifying at the end. So the first one here we're looking at is simplifying. So a to f is just simplifying using the rules. So if we look at 3a, the first thing it says is to simplify log x plus log y. So if we look at page 21 in our tables, we can see that that is this rule here in the middle. Log x plus log y to any base is basically written as log x times y. Now, when there's no base written, that base is always assumed to be 10. So just a reminder, we just say note, log x is the same as saying log x to the base 10. So that is always the case. When there's no base, the base is always 10. And that's it, simplified. So second one then is where we have in B log 3x, and this time we have base 2, minus log x to the base 2. So before we can apply any of these rules, we always have to make sure that the bases are the same. And again, when the bases are the same, you can use all of these rules. If the bases are not the same, you'd have to change your base, which is the one I've just put a box around up here on page 21 in your maths tables. Again, it's rare that we'd have to use that really in differentiation. That's more in algebra, where they're testing your log skills. Whereas in differentiation, they're testing your differentiation skills. But of course, you need your foundation in your algebra to be able to simplify or finish off your question or even begin the question. So which rule is this? So we have a minus this time. So if we look at our maths tables, we can see that's actually going to be the second log rule there. And when we're subtracting our logs and the bases are the same, it's the same as writing it as x over y. So in other words, log 3x over x to the base 2. And of course, x will go into x there, leaving us with log 3 to the base 2. Okay, so in C then, I'm going to the next page, is log 1 to the base 5. And if we look at our tables, page 21, we'll see this rule here, the fourth one down. It says log 1 to a, base a being any base. So log 1 to any base is always going to be 0. So even though we have log 1 to the base 5 there, the answer is still going to be 0. And of course, you can put that into your calculator there, and you will also find that you get 0. So D then is log 0 to the base 2. And there is no rule here on your tables dealing with this, but if you put that into your calculators, you will get maths error. In other words, it is undefined. It is not possible to get log 0 to any base, and that's because we can't get 2 to any power to give us 0. In other words, any number to any power will always give us a number. It'll never give us 0. So E then, if we go back, is ln And again, this is a really important one. ln is the same as saying log e to the base e, and log of any number to the same base is going to give us 1. And again, it comes from this rule over here. Log a to the power of x to the base a is equal to x, because again, if I bring that down, if there's a number raised to the power, that can actually be written as x times log a to the base a, and you can see that that's x times 1, which gives you x. So in other words, this log a to the base a is always 1. So therefore log e to the base e, or natural log of e, is always going to be 1. Okay, so f is log 4 to the base 4. So therefore that follows on from ln e. In other words, log 4 to the base 4 is also 1. Log 10 to the base 10 is 1. Log a million to the base a million is 1. Always the case. Okay, so G and H then, this time rather than simplifying, we want to expand using our laws of the logs. So we're going to be reading left to right rather than right to left this time. So we can see we have log 3x minus 5 over 2x. And again, no base is given, so that's just assumed to be the base 10. And if I look, this is the second log rule on page 21. So in other words, this is the same as saying log 3x minus 5 minus log 2x. So if I was to expand, that's what it would look like. And the last one then is h. And h is log y squared minus 3y over x. And again, same rule, log y squared minus 3y minus log of x. So always just being able to expand or simplify your logs is going to be really important when we do our differentiation. Okay, any other issues, make sure you're asking, please.